Most languages are not made for the precise communication of ideas. For example, in the English language, the word few can take on several different meanings depending on the context. It can mean anything from 2 to 7 to 10, though most people generally agree that few means less than 10. Math is a way to communicate ideas precisely using agreed upon notations and conventions. These conventions are usually called axioms, and they form the foundation of our thoughts. We use these axioms and logic in order to create new ideas from our basic assumptions. Math can be used to describe any number of fields, from the arithmetic that you learn in school to more abstract things such as abstract algebra or hyperbolic geometry, even subjects that you might not have even heard of, such as combinatorics or complex analysis. But more than any one of these specific fields, mathematics is a way of approaching a subject, and it's a way of thinking about different things. It's using logic and precise communication in order to make sure that everybody is able to understand and talk about the exact same concepts. As an example, consider the definition of continuity. What does it mean for a function to be continuous? Well, if we look at this graph, the blue lines are what we would call a function. Intuitively, we see that there's a jump at the point that's labeled x sub 0, which we usually read x naught. This jump is called a discontinuity. But how do we describe this mathematically? What can we use to say that covers all sorts of different situations where a function might not be continuous? Any person who sat in an undergraduate real analysis course will probably recognize this definition. It means, using various mathematical notation, that the function f mapping the set from a to b to the real numbers is continuous if for every epsilon greater than 0 and x in the interval a to b there exists a delta greater than 0, such that for t in the interval a to b with the distance from t to x less than delta implies that the distance from f of t to f of x is less than epsilon. Essentially, a small change in the input will mean that there's a small change in the output. So taking this step by step, we look at this first part. This notation is very common. You have a symbol to the left of a colon, and that denotes the name of the function. Here, our function is named f. And the first part to the left of the arrow tells the set that the function acts on. In our case, we're talking about real numbers, and these brackets mean that we start at the number a and we end at the number b. Because they're closed brackets and not parentheses, that means that we want to include the numbers a and b in the interval. If they were parentheses, that would mean that we can use any numbers that are very, very close to a and very, very close to b, but we can't use the numbers a and b themselves. The letter to the right of the arrow, it looks like an R, that's because it is an R, is called math boldface, Blackboard bold, and it's used to denote the set of real numbers. Because we talk about the real numbers a lot, it's very convenient to have one symbol that everybody agrees means the real numbers. And the rest of this is just English. We're like starting a definition. Now we go on to this next part of the definition, and we have a big curly brace here on the left. I'm using this as shorthand to say that we want to take these two conditions together. So this upside down a is called the universal quantifier. It sounds complicated, I know. But what it just means is we want to say that the statement is going to be true for every possible value of epsilon greater than 0. And then the part underneath it is just notation. The e means n, so we're going to take any number x that is in the interval from a to b. So we take those two conditions together. So we say that a function is continuous if for every epsilon greater than 0 and x in the interval from a to b, this backwards e means there exists delta greater than 0. So this says for every epsilon greater than 0 and x in the interval from a to b, there exists a delta greater than 0, such that we move on to the next part. Here we're going to use the giant brace again in order to say that we want to take these two conditions together. We're going to have any number t in the interval from a to b, and here we have some notation that means absolute value. Absolute value is essentially denoting the distance between two objects. So here when we say x minus t, the absolute value of x minus t is less than delta, what we mean is that the distance between x and t is less than delta. And that together implies, that's what the big bold right arrow means, that the distance between f of x and f of t is less than epsilon. So if you remember from earlier in the definition, we're going to say we pick an epsilon and we pick some value x, and then for those two values there's some delta that makes this condition true, that says when you pick a t that's close enough to x, then you can make the outputs arbitrarily close to each other. Essentially, a small change in the input means a small change in the output. You'll notice that it looks really complicated and hard to say something that seems obvious when we can just look at it. Mathematics is made to handle these kinds of situations. We want it to be very precise and make sure that everyone is communicating the exact same ideas. Thank you.